So, yeah. Hello everybody. Again, sorry for the delay because of some technical problems. We were not able to start in time. So uh, before starting today's webinar, I would like to confirm if you are able to hear me. So if you are able to hear me properly, you can type OK in the message window. Okay. Okay, so let's start today's webinar on product introduction of Midas Civil and its general use. Okay. Today we'll be looking at the overview of Midas Civil, then we'll go into modeling features of Midas Civil, how to apply boundary conditions, load conditions, and check the analysis results, and see some of the design features in Midas Civil. So Midas Civil is a 3D-dimensional finite element modeling package and provides a very powerful user interface and solutions for all kinds of bridges. When I say all kinds of bridges, these are the important types of bridges which Midas Civil can provide solutions for, starting from slab bridges, culverts, going to composite type of bridges, and based on the method of construction of the bridge, analysis can be done, simulating that particular method of construction. For example, balance cantilever method of construction, incremental launching method of construction, etc. Then coming to complex type of bridges, like cable bridges, such as cable stayed bridge or suspension bridge. Then apart from bridges, there are some special structures which Midas Civil provides solutions to. For example, underground structures, and you can also model soil structure interaction in the software. And if you want to do detailed analysis such as crack section analysis and computational fluid dynamics analysis, we can go for a more detailed finite element modeling in the sister software of Midas Civil known as Midas FEA, and we can perform the analysis there. These are the most important analysis types that are performed in Midas Civil, starting from the moving live load analysis, then construction stage analysis, which can consider the time dependent effect, then going to the large displacement linear analysis, P delta analysis, then geometric nonlinear and material nonlinear analysis. And for the seismic analysis, the program provides for pushover analysis, time history analysis, and response spectrum analysis. For any type of modeling of a bridge, we use a variety of softwares. Which provide different elements to model the bridge. So normally for a preliminary analysis, for a simple analysis, we go for one-dimensional elements to model the girders. They may be like truss elements, cable elements, compression only gap elements, or beam elements. But when we want to do detailed analysis and we want to check local stresses, then we go for plate modeling or solid modeling. So there are 3-noded and 4-noded plates available. And for solids, we have 4-noded solids, 6-noded solids, and 8-noded solids. One of the most important features of Midas Civil is the powerful graphical user interface. In the graphical user interface, the user can model and analyze and design the bridge in a very intuitive manner. For example, let me show you how easy and how useful the interface is. This is how the blank screen of Midas Civil looks like, and this is the graphic user interface you can see. On the top we have the menu bars, and which consists of all the options required for modeling, analysis and design. Then below that we have the tabbed toolbars. These are the shortcuts to these menu bars. Then we have several icons which again stand for these shortcuts to these menus. Then we have various kinds of selection tools. So depending upon your situation in the complexity of the structure, we can select any part of the structure in a variety of ways, whether select by polygon or select by windows or select each element according to its property. Then on the right side we have various display tools, starting from the zoom tools, the panning tools, and various display modes such as various views such as isometric, top view, side view, etc. And then on the left side we have the tree menu. In the tree menu you can see various tabs are present. So these menu tab contains the same options that are available in the menu. Then we have the various tables which will list out all the information that you have inputted in the software to create the model in a tabular format. So and the best thing is that it is compatible with Microsoft Excel, and you can edit the tables through Excel sheets or copy the tables in the software to the Excel sheets. Then there is a group tab to create various groups which will be required in the construction stages, as I will demonstrate in the example model today. Then there is works tree. The purpose of this works tree is to list out all the works that you have performed till now in the modeling, or that you are performing for the analysis. You can list out those works here, and if you want to edit anything in the model, this is known as the model view. If you want to edit anything in this model view, you also have the option for just drag and drop the particular work from the works tree to this model view, and within an instant the model would be edited. And also, if you right click in the model view, there is this context menu. From here also you can access the various options. So let me show you an example. So for example, you want to apply a point load on a particular structure. Then there are various ways. So let's start with the menu load. You go to nodal loads, and you can apply nodal loads here, or you may go to the tab toolbars here, load, go to nodal loads and apply nodal loads. Then you can also go to the tree menu bar, go to static loads, and here nodal loads, and here you can access, or you can right click in the model view and go to load and nodal loads, and you can access it from here. Or for users who are very comfortable using commands to model and analyze, Then for them you can also write command in the command message window. So let's write, for example, you write the command for nodal loads and press enter, and again the same option. So there are about 5 ways of accessing any feature in the program, which makes it very user friendly. So as I was discussing about modeling a bridge in various CAE softwares, you require elements to model a bridge. So there are various ways of modeling a bridge using elements. You may model the bridge using step-by-step element modeling, or you can directly model the bridge by one click by using wizard. And the wizard's purpose is to automatically create the model, the elements, apply loads, and apply boundary conditions at just a click of a button. So on the screen you can see the wizards used available in Midas Civil, starting from the RC bridge wizard, then the grillage model wizard to create the grillage model of a bridge. And based on the method of construction of the bridge, there are several bridge wizards which will automatically create the construction sequences, starting from the FCM wizard, known as also called the balance cantilever method bridge wizard, then the FSM, which is the full shoring method bridge wizard, then ILM is the incremental launching method bridge wizard, and MSS is the movable scaffolding system bridge wizard. Then for cable bridges, you have suspension bridge wizards and cable straight bridge wizards. So here I will show you an example of the balance cantilever bridge wizard. So here model structure wizard. You can see all the wizards that I listed in the PowerPoint. So let's see, for example, the balance cantilever method bridge wizard. So here you can see that you have a geometry in the display of the FCM bridge wizard, and it is asking for some basic inputs like material of the girders. So let's say I enter the material for the girder as concrete, and you can select the code and enter. And the pier also, let's say same, and I enter the number of piers, let's say 2. And let's say the pier section I can enter from here. And I can enter the stage duration here, the duration of each stage. The method of casting of the girders can also be inputted here, whether cast in site or precast. And then you can enter the section dimensions from here, section dimensions of the girder, and also the section type, 1 cell or 2 cell. And then go and define the tendons, the pre-stressing tendons from here. So the internal pre-stressing tendons and the external pre-stressing tendons can be defined, and just entering a tendon property. So in the tendon property you can enter the type of pre-tensioning, the type of pre-stressing, whether it is a pre-tensioned cable or post-tension cable, or it is externally pre-stressed cable, let's say internally pre-tensioned. And you can choose the material of the cable from here. So steel, say and you can give the tendon area and various loss parameters. For relaxation loss, you can give the parameters here. Then for friction loss, for anchorage loss, etc. And when you click on OK, you can see that the just entering a few basic inputs, the bridge is modeled, and in the tree menu on the left, the works tree, you can see all the works that have been performed till now, starting from the nodes or the points that have been used in the model, and the elements. There are 78 beam elements. Then the material properties that have been used in the model, the sections that the wizard generated. Then we have the boundaries. Let me display the boundaries. So you can see the fixed supports and the pinned supports here. Then the bearings. These are the bearings at the top of the piers. Then the loading, the self-weight, the pre-stress loads, the form traveler loads. For example, this manner, the form traveler loads for each construction stage have been automatically defined. So just by right-clicking these options, you can display and undisplay them. Then the tendons, the various pre-stressing tendons are defined. For example, if you want to see the tendons, right-click and display, and you can see these gray lines. These are the tendons. I'll switch off the 3D view. This is the actual view of the structure. So I'll switch off this, and now it is just a line model now. And you can see the tendons clearly. There are these many tendons that the program automatically generated using the wizard. Then since this is the FCM wizard, it should be able to simulate the balance cantilever method of construction. So let's see if it does that or not. So go to stage here, and you can see all the construction stages. The base is the final model which we make regardless of the construction stages. So starting from construction stage 1, you can see only the piers modeled, and then gradually the balance cantilever construction starts, and this is how the bridge is being constructed. So automatically the wizard can model the construction sequence for you. This is the advantage of using a wizard, because it helps you in reduction of time in modeling. Plus, if you want to do any kind of parametric study on the bridge before finalizing your model, then you can use wizards. It is a very short way of doing such a preliminary study without having to model every single beam manually. So this was about the automatic modeling using bridge wizards. Now there is one more way of modeling a bridge in Midas Civil. That is, if you have already created the profile of the bridge in AutoCAD file or in AutoCAD and saved it as DXF, then you can import that model in Midas Civil and continue with your load application and boundaries, and then perform the analysis in that. So let me show you how to do that. So I'll start a new model. So here you can start the new model by either going to File, New Project, or clicking on this icon. So when I go to File, I have Import option. You can see Midas Civil can import from these many softwares, and we are interested in right now in AutoCAD DXF file. So here I just called in the the DXF file, and before the import it is necessary to take care of the units. You can change the units at any time in the program using the status bar. Here you have the units displayed, so you can change it, force unit and displacement unit. So before import it is necessary that you change the units to the same unit with which you used while modeling the bridge in AutoCAD. So here you can either define the material properties and section properties here itself or later on. And if you click on OK, you can see that this cable stayed bridge model is automatically imported into the software directly from the AutoCAD DXF file. However, there are some rules which users should follow before importing a DXF file to Midas Civil. The rules are like all the lines, if you have used lines in AutoCAD, they are imported as beam elements. Surfaces are imported as plate elements, and solid, if you have solid cannot be imported from AutoCAD DXF. And most importantly, the unit system must be consistent. The same unit system should be used for import. Then after generating the geometry, creating elements or by either wizards or by import option, we want to now insert material properties to those elements or beams. So there are a variety of ways to do that. So first of all, Midas Civil has included many international codes. The database from the material database of these codes have been implemented. And not only the database, but also you can define the material from your own side. Then secondly, for the construction stage analysis of a bridge, and especially for the post-tensioned analysis of a bridge, the time-dependent material analysis is very important for calculating the creep shrinkage effects and the time-dependent for calculating the time-dependent variation of the compressive strength, plus to calculate the time-dependent losses in the pre-stressing tendons. It is important that we input the time-dependent material properties. Well, this can also be done in the software, and again through various codes, database from the codes, or as user-defined. So let me start by today's example model by entering some material properties. Okay. So to enter the material properties, you can either go to model and properties and material, or you can just right click on the model view and properties. You can access it from here, and material. So here you can add. So we are going to model composite plate girder bridge. So I'll enter you can see based on the type of the design, you can select the material type. So let's say I want to define one steel material. You can select from the code database, and these values you can see automatically get entered the material properties. So you can apply, and let's say a concrete, and again apply, and let's say a steel SRC type of material. Here again you can choose the material properties of concrete and steel for the SRC material, and you can again, let's say I name it, you can change the name from here. Composite material, and apply. And if you want to enter a user defined, you can do that. So just select user defined, and here you can enter the material properties of modulus of elasticity and weight density Poisson ratio from your own side. Plus, if you want to do material nonlinear analysis, that is, you want to enter the plasticity data for the material, you can do that. The plastic material can be defined from the properties option, and here you can input that plastic material that you have entered. I'll show you. So right click, properties, and here you can go to plastic material and you can select the type of the material. So for example, if it is steel, then the material model you can select as von Mises. You can enter the material properties and apply and give a name to it, and you can select that name in the plasticity data. So these materials are now defined. Now I want to also include the time dependent material properties. How to do that? Again, model properties. Here you can go to time dependent for creep and shrinkage and time dependent for compressive strength. So creep and shrinkage, here add, give a name to this time dependent material function for creep and shrinkage, select the code from here, and you can enter the compressive strength. So let me change the units first. Now properties. And for the concrete, we are going to give the property to concrete. And enter the notational size used for the calculation of creep and shrinkage, for the calculation of creep. And if you click on show result, you can see the variation of the creep coefficient with time and also the shrinkage strain with time. And using these options, the start loading and the end loading options, you can vary this tabular format of tabular data. You can vary this tabular data using these values. So if you increase the number of steps, this data would be affected. This is just for a better interpolation. And okay. And then again properties, and now compressive strength function. So again you can select the code from here and enter the compressive strength, the mean compressive strength, and you can select redraw and see the variation of compressive strength with time. And if you don't want to use the database, you can also create your own function, own creep shrinkage function using time dependent material creep shrinkage function. Go to creep, add, you can enter these values here, time and value, creep function, whether you want to enter specific creep function or creep coefficient. You can do that from here. Then these time dependent material functions are created, but these are not assigned to the particular materials. So to assign them to those materials, you can go to properties, and here you can go to time dependent material link, select creep and shrinkage function, compressive strength function, select the material to which you want to assign these functions, and add. So now this concrete material is assigned with time dependent material property, and when we do the construction stage analysis, we will see the effect of creep and shrinkage on this material. Then after defining the material properties, we define the section properties which we will use in the model. So again, Civil provides the users with a variety of sections. So if we start from, we right click properties, section, and here we can see add. So starting with the standard sections, like I sections, T sections, angle sections. Again, these sections can be either user defined like this or taken from the database by clicking on this, select the code and select the type of section from here, and automatically they get entered. Then you have this option of offset. So right now by default this offset is set to center. The meaning of this is that if you model element and provide this section to this element, then the element which is represented like a line, that line would start from this point, not from the top, not from the bottom, but from the centroid. But when you select center top, then you can see this red dot, the element, this is the centroid. So earlier it was starting from the centroid, the line, the beam, the reference line, but now the reference line would indicate this top fiber of the section, and so on. There are many kinds of offsets like top centers, right center, left center, etc. So depending upon the situation you can use these offsets. So let me model the cross beams here, which I will be using in the model. Cross beam and dissection. Now let me select let's say center bottom. Okay, so this the element, the cross beam which I will create will the reference line will represent the bottom fiber of the I section. Then there are value type of sections. So for irregular sections or the sections which are not available in the database, you can directly enter the section properties from here. So I didn't input the cross beam, so I'll just apply it here. So my cross beam is applied, and you can see the section properties of this section by clicking on show calculation results, and you can see the area, the effective shear area, moment of inertia, and the centroid, CYP, CYM, PM. Well, P and M represent the top, bottom, and the right and left respectively. So for example, CZP is the location of distance of the top fiber from the centroid, and CZM is the location of the bottom fiber from the centroid, the distance of the bottom fiber from the centroid. Similarly, CYP is the distance of the rightmost fiber from the centroid, and CYM is the distance of the leftmost fiber from the centroid. Then for each section, program creates what is known as stress points. So generally it creates four stress points for a normal section. For pre-stressed concrete box cutter sections, it creates 10 more than 4 stress points. You can create by default 10 stress points. So for normal simple sections, it creates 4 stress points. What are stress points? These are the locations at which program will calculate these stresses, and like you can see there are 4. That means for each section there will be 4 locations at which program shall calculate these stresses. So when you see the result beam stresses in the program later on, then these are the locations 1, 2, 3, 4, and the coordinates are given here. These are the locations where the stress would be displayed. So then we have SRC type of sections, then combined sections, that is built up sections used for steel structures, then pre-stressed concrete sections. So here we have PSC 1 cell, 2 cell, 3 cell, also PSC value. So for example, you can select the model the PSC section either from the code, select the code, and the section will be displayed here in the PSC viewer, or you can directly model it by entering the values by seeing this diagram. and you can enter these design data required for the design here, and also for the PSC value sections. Just like value sections, PSC value sections are used to model irregular PSC sections. You can enter the section properties directly from here, or you can define the section using coordinates. So you can enter the coordinates here, and the section gets defined automatically. So you can enter the coordinates, and this polygon can be formed, which will represent the PSC section. Or you can also import from SPC. So I'll explain about SPC later on. SPC is the section property calculator, which is used to model any irregular type of section and export it to Midas Civil for analysis. So if you have a section that is modeled in AutoCAD, you can import that section in SPC, and SPC will calculate the section property, as the name suggests, section property calculator. It will calculate the section properties, and it will again export it to Midas Civil, where we can do the analysis using that section. Then we have taper sections. So any type of section, we can connect them and form a taper between them. So if you, let's say you want a solid type of section taper, you can define two solid sections with different dimensions at two ends of the elements, like this, one end and the other end, and you can give the variation, whether parabolic variation or linear variation of the taper, and the tapered section would be created. Then we have option for composite section, which we will be using. So we can create a composite steel box type of section, or composite plate composite plate girder section, composite I, and composite T, and composite PSC. And if our section is irregular, we can go for composite general. We can again import the section from a SPC, section property calculator. So let me define a composite steel I type of section. So my main girders will be of composite steel, and if I will model two girders, two composite plate girders. So the total slab width containing the two girders I've entered here, the number of the girders, and the center to center distance between those two girders. And this is the individual dimensions for a particular girder. Now this data which I have entered here, this is used to calculate to increase the lateral stiffness of the bridge, because when we have a composite, when we have two steel girders and a composite slab, then the slab has stiffness in both the directions, but when we model a beam element, it only considers the stiffness in the longitudinal direction. So to increase the stiffness of the deck in the lateral direction, to consider that stiffness, this value has to be entered. So this is using this, the program will calculate the lateral stiffness and will increase the stiffness of the bridge. And now this is the individual girders dimension. This is the height of the shear connector, and we can, this is the height of the web, the top flange width, the top flange thickness, web thickness, bottom flange width, bottom flange thickness. And then for the calculation of, since it has two types of materials, A composite section has two types of materials. So to calculate the initial stiffness, to calculate the short-term stiffness, the program needs to know the modular ratio due to the two materials. So here we can define the material properties. So for the concrete, let's say this is my material, and for the steel, I enter this, and you can see automatically the modular ratio is entered. You can also edit it and enter your own modular ratio. This is the density, weight density ratio, the Poisson ratio for steel, Poisson ratio for concrete. And this one here, we want a center offset. So the centroid will represent the beam line. And now when you click on calculation results, you can see the before composite stiffnesses and after composite stiffnesses. So the before composite stiffnesses is the stiffness of only the eye girder, and the after composite stiffness is the stiffness of the concrete slab plus the eye girder, taking into account this modular ratio. And I click on OK, and this section has been entered. Now since I was talking about the SPC, so let's say what an SPC looks like. So tools, section property calculator, and here we can select the units. And just like any other modeling interface, it has a works tree here and various geometry options for creating curves, boxes, and you can also get a grid here. And you can draw the model here, or you can import from AutoCAD. So let's draw the model here. So let's draw a PSC value type of section. That is a PSC irregular section, which is not available in the database of the software. So create on the works tree. You can also go to model, curve, and create. So create and polyline. So this is created, the outline, and now I'll generate the section. Section generate. You can choose to fill all this section or create a hollow section. I want a plain type of section which will fill all this inside this, and enter the name of the section, PSC section, let's say, color, and select and apply. So my section is generated. I could have calculated the properties from here also while generating the section, but let's see what is the other way for that. So go to property. Now only the section is created. To calculate the properties of this section, go to calculate section properties, and here you can see there is a term called mesh density and mesh size. So why this feature, why this mesh size? You can see in the presentation. So the properties like area, the moment of inertia, centroid, they can be calculated using standard formulas, and but the calculation of properties such as torsional moment of inertia or the effective shear area, the shear areas, they don't have any standard formula for all types of sections. So for irregular type of sections, finite element analysis is done. So if you enter the mesh size, the program will create an element, and internally it will create an element having that mesh size length equal to the mesh size, and apply a fixed support at the end of the element, and a unit load is applied at the other end, and then does the analysis and calculates the torsional moment of inertia and the shear areas. This is the use of this mesh size. Select this, apply. So the section properties are generated. And now if you want to see the properties, then you can right click property and display. You can select any properties. Let's say effective area. Effective area is generated, moment of inertia, and so on. And now this section is ready for export to Midas Civil. So file, export, model, section, and here export section. Select Midas section file. Give a name to this section. Say PSC and save, and select this and apply. Now then return back to Midas Civil. I'll just save this this model for once. And properties section, add PSC, and here select PSC value, section data, import from SPC, select the newly created section from here, OK, and you can see this section is imported. Here the properties can be seen from here, and so on. You can use this section now. Just click OK and give a name to it. You can use the section. So this is how you can model any type of section in Midas Civil. So after seeing the after generating the materials and the sections, now we go on to generate the elements or the beams. So there are a number of ways you can generate elements. So either you can first generate the points, endpoints, and connect them point to point or node to node, or you can generate a grid, just like you saw in section property calculator. There was a grid, and connect those grid points. You can do that. Or you can also create elements on curve. So if you have a horizontally curved bridge and you want to model it fast without entering the coordinates of the nodes, you can do that by entering as an arc by 3 points or circle by 3 points and parabola by 3 points, etc. Or you can also generate larger elements, larger order elements from a smaller order element. So you can generate a line element from a point, and from a line element you can generate a plate element. From a plate you can generate a solid element. Let's see briefly how these features can be used. So let's first let me show an example of a grid by grid modeling. So you go to grid here, you click on you can just click on this grid snap option. Just click on point grid here. You have the grid here now displayed, and now right click elements, create elements, and select the element type. Let's say general beam. We want a beam element, material name, the section name, and then start connecting these points here to here like this, in the same way, this manner. And you can see this section, I section, is entered here. And if you want to create node to node, so I'll switch off this grid now, and let's say I undisplay the 3D view, and elements, create elements, and just click on this nodal connectivity option and just connect, click the nodes which you want to connect like this. You can do that, but I'll show you the method by wizard, how to create the elements by wizard here at just one click. So I'll undo this thing. So this option is used for undoing. So you can just click on this arrow. You can select up to which stage you want to undo. There are unlimited undo options here. So up to, let's say, add nodes, I want to undo. Okay. So all the steps up to that have been deleted. And now go to model, structure wizard, frame. Here we can generate the frame. So select, enter the distance, let's say x coordinate has been entered. The other dimension can be entered from here. And then edit, I select the material, composite type of material, let's say cross beam material, that is steel, and the section has cross beam. And then generate the frame, then go to insert, and here since it was in XZ plane initially, so I want to rotate it by 90 to bring it to the XY plane. So now this will be rotated, and click on OK, and you can see this is modeled at one go without having to connect node to node. Now I want another a third girder here. Let's say if I would have wanted that, then I can also do that by elements, translate elements. So if you go to translate, and you can select the required elements you want to copy. So just from left to right, select like this, and here you can enter the distance. You have to select copy here and enter the distance through which you want to copy. And apply. So you can see that all these selected elements are now copied. So I'll undo it. I only want two girders, as I enter the section properties for two girders. This view, this XY shows the global XY coordinates. Let's undisplay it for a better view. Okay, now it is clear. And switch on the 3D view like this. So here we can see that you can see that the center bottom which we defined for the cross beams, these are all inputted as cross beam sections. So center bottom, you can see that the bottom is connected, or everywhere the bottom of the section is used for the element. And now let me change these main girders into composite sections. So I'll select the main girders. To select the main girders, just click on this option, select, and clicking and draw a window like this, and everything inside the window gets selected. And from here, choose the material, composite, and just drag and drop to here. So this main girders have been assigned with composite type of material, and now I want to assign the sections also. So just click on this button, which is for select previous. So the previously selected items will be selected again, and click on main girders section and drag and drop here. And you can see how my section is now changed to the composite section, which I want. You can see from the side view, this is how it looks. This is the transverse girder, the cross beam, and these two are the composite slab girder system. Okay. So when we model this element, we may make mistakes. How to correct those mistakes, or how to edit some of the parameters of an element? There are mainly three ways. We can use the element table to do that. Let's see. In the model, elements, you can go to elements table. You can see a number of elements, the type of the element, beam type. You can change the type from here. You can change the material number. So like composite has been assigned 3 number. So 3 is selected here. You can change it to 2 and it will get assigned with this material. Then similarly section property and many other uh, parameters can be changed. The coordinates, the nodes can be changed. The other way is I showed you just now through the works tree. So I just changed the section of this main girders by just dragging and dropping from here to here. So that is another way. And the third way is right clicking, go to elements and change element parameters. And the change element parameters, you can again change the material ID, the section ID. You can rotate the element about its local axis. This is used to give a super elevation to the bridge. And you can also change the element type from, let's say it is beam, you want only truss elements which do not allow any movement. You can do so. Select all these elements and just click on apply and they will be as treated as truss elements. Then there are various ways to enter mass in the structure. So first is when you enter the material properties, the program automatically included the mass density here. So when you define the self weight for the structure, program will automatically assign the mass to the structure using that mass density. The other way is go to model, masses and nodal masses. So to each node you can provide some mass. This is used when we are trying to do the dynamic analysis. We need to do a the model analysis before that, which is also known as eigenvalue analysis, to calculate the mode shapes functions or the participation factors. And for that we need to lump the structure mass at the nodes. So this is done using this option. I just want to pause for a bit. Mr. Sonai has asked a question. How did I move the cross girders above, that is from below the girder to below the top flange? Well, as I mentioned, this is due to the offset function. You can change the position of the element according to this offset. For example, I'll show you here. If I select this cross beam and I go to the section for this cross beam, here there is a center bottom allocation. So the element line will represent the bottom of the section, and if I change to center, now it will overlap with the slab. You can see all the cross beams overlap with this concrete slab. So I'll undo it again, and this is how you can change the orientation. Also, not only it is fixed with center bottom or center top, you can give a particular distance. So for example, a vertical offset can be given, a distance can be given, and according to that the element line will shift to that particular location in the section. Okay. Okay. So I was talking about the masses, two nodes. Now nodal mass was one of the options. The other option is loads to masses. So any type of live load or dead load except the self weight can be converted to mass at the nodes using this loads to masses option, and you can choose the mass direction to the direction in which you want to apply the mass, and these are the various loads which can be converted here. You can select the load case and apply. To convert the self weight to nodal masses, you go to model structure type. Here you can convert self weight into masses. So convert to XYZ, convert to XY direction, convert to Z. You can select and click on OK, and self weight will be converted to masses for conducting the eigenvalue or modal analysis. And on the top you can see the structure type. Here you can select the type of the structure. Let's say you don't want any deformation in the Y direction. You can select the structure type as exit and perform the analysis. So this way you can also constrain, let's say RZ. You don't want rotation about Z, constrain it. And so there are a variety of ways you can define a structure. So after defining the elements, now we'll define the boundary conditions for the elements. So starting with the most ideal boundary conditions, that is the supports. You can define supports like fixed support, and you can also define pinned supports. So for defining supports, right click, go to boundaries, supports. Now you have here dx, dy, dz, rx, ry, rz. Just click on the particular degree of freedom to restrain that degree of that movement. Then in most of the situations we have non-stiff boundary conditions, that is the soil, which you cannot model with ideal supports. So therefore we go with the point spring supports. We can apply stiffnesses to the supports. There are various kinds of spring stiffnesses, or in various manner we can define the this point spring supports, starting from linear point spring supports. Let's see boundaries and point spring supports. So starting with linear, where you can give the stiffness in all the 6 direction of degree of freedoms. This is how the spring looks like internally. The program considers this type of spring with 0 length, and stiffness can be provided. Or you can define a compression only a spring. Now this is used to model the bearings, compression only springs. Or you can also define multilinear springs to account for the non-linear force displacement relationship of the soil. So you can enter the various coefficients, and this graph will be generated for the multilinear stiffness of the point spring support. How to assign this point spring support? Well, just select the particular node and you can enter these values and click on apply, and this will be assigned. I'll show you here how to do that in just a couple of minutes. Then we have surface spring supports. This is used to provide spring stiffnesses below a surface. The previous one, point spring supports, was only for a node or a point, but this one is for, let's say you have modeled the footing as plate elements and you want to apply the supports throughout these plate elements, not just at the points. You can do that. So again, to access this option, go to boundaries, surface spring supports. Here you have option whether you want to change this spring supports as a nodal spring or as a distributed spring. So when suppose this is a plate and you have 4 nodes here, so program will divide it into areas, and this formula is used, multiplying the modulus of subgrade reaction with the effective area. It will distribute it to these end nodes. Again, there can be linear type of stiffness provided, compression only and tension only. Then you have distributed spring, which provides springs throughout the surface. So select the face and enter the subgrade reaction, and the total area will be multiplied by the modulus of subgrade reaction, and stiffness will be calculated from that. Then elastic links. Elastic links are most commonly used for modeling the bearings in a bridge. Also, if you have a rail structure interaction, then elastic links are used to simulate the multilinear or the non-linear characteristic of the ballast of the rail structure. So when you see this model here, we have the pier, and on top of the pier sits the bearings, and on top of the bearings sits the girder. And here we have used center top type of connectivity, top type of a section. Hence, the beam reference line is at the top, and that is connected rigidly to the bottom of this section by using rigid link. And from those bottom 5 points, we drop the elastic links connecting the pier with, such that they represent the bearings. Again, we can enter the various stiffnesses for the bearing, whether compression only, tension only, rigid, general, or in case of raised ballast, we can enter the multilinear elastic links. For example, here we have the rail structure interaction shown, the ballast, the rail, and the bridge deck, and this is the stiffness that we want to provide here, and we can do so as shown here. Then we have beam end releases. Beam end releases are used to release a particular force at either ends of a beam. So let's say you're doing a composite construction, and in the first stage you have installed the precast beams, so they are all simply supported, and you don't want moments to be transferred like this to each other, to the other portion. So we provide beam end release at the ends like in this manner, and you can see the moments are not transferred. But later on, when the deck is casted, then the beam end releases are removed, and then the moment can be transferred like this. So in this way you can simulate the construction process. Then rigid links. Rigid links are used to connect any two nodes rigidly, that is to avoid any kind of relative deformation between two nodes. How it is done? Well, one of these nodes becomes the master node, and it controls the deformation of the other node, which is also known as the slave node. And you can choose which degree of freedom to control using the master node, dx dy dz and rx ry rz. For example, in this figure, this beam has been modeled in two ways. At one end, it is just a line element, beam element, and in the middle it is modeled with plates. So to ensure that this point, which is representing the center of this line, is connected rigidly with the plate model, to do that, this node was made as a master node, and all other plate nodes here were made as slave nodes, such that now there is no relative deformation between this node and these nodes here, and they act as a part of the same beam. Similar thing we'll do in this model also. We'll create the points at which we want to provide the supports. Let's see. So here I want to give bearings below the bottom. So I'll copy the nodes here, here, and here to represent the bottom of the section node. And to see how much distance I need to copy them, I'll see the distance from the bottom fiber. You can see that the distance from the bottom fiber is 995 mm here, and I'll provide this distance to copy these nodes, translate, copy in the Z direction, -4, and also I want to give bearings below that, so another 500 mm, and apply. So you can see that the bottom of the section point and the bearing endpoint have been generated, and now I'll connect them with rigid link and elastic link. So go to boundaries, rigid link, and here select rigid body, and before doing that I'll create a group first for the boundary. So right click, new boundary. I want to use these boundaries in the first construction stage for this bridge, where it will have only steel girders, and similarly I create a structure group for my main girders and another structure group for my cross beams. So now when I select boundaries, rigid link, here I'll select the boundary group, and master node, that is the controlling node. This is the topmost node I'll select, and I can also copy the rigid link directly from here to any other point. So let's say in the X direction 50 meters and rigidly connected, and choose the slave node from here and apply. So you can see that in the Y direction it is copied. This is a master node for this node, and similarly this one for the other node, and similarly in this end also I select this one as a master node, and again select this slave node, apply, and all 4 rigid links have been created. Then I'll define the bearings, boundaries, elastic link. Under the same boundary group, I want to use all these boundaries in the first stage, so I created only one boundary group. Groups are necessary for activating a particular feature in a construction stage. So you can enter different types of elastic link data. General elastic link enables you to enter the stiffnesses in all the 6 degree of freedoms for the spring, and a rigid type of elastic link provides a very high stiffness to the link, almost 100,000 times the stiffness of the largest frame element, the maximum the most stiff frame element in the model. So here you can select the 2 nodes, and just select the 2 nodes from here. You can see the elastic links have been created. Again select it like this and see the other elastic links created. So the 2 bearings are now modeled, and now it's time for modeling the supports. I'll go for the point spring supports. The point spring supports, again a boundary group, a linear type of point spring. I'll change the units and enter the stiffnesses. Okay, let's say I apply the same type of support at all the ends. Select the nodes, bottommost nodes to which you want to apply these supports, point spring supports, and apply. So these black ones represent the free degree of freedoms in this hexagon, and the other parts represent the constraint or the stiffened degrees of freedom. So my boundaries are assigned now. And if you want to see all the boundary conditions, just click on this button, go to boundaries, select everything here, tick on this, and you can see all the boundary conditions. You can display this, and let me change the view, and you can see this is the rigid link, this is the elastic link, bearing. This rigid link connects the center of the main girder to the bottom of the main girder so that they act as one section, and then this support here. Okay. Then non-local axis is used in the case of horizontally curved bridges to obtain reactions in the tangential direction. So this rotates the local axis of the support node, and reaction will be obtained in that direction. Then we can also obtain the effective width, automatically calculate the effective width scale factors for the various girders in the program. Just go to boundaries and effective width scale factor. You can enter the effective width scale factor here. This will affect the stress calculations. You can change the moment of inertia from here and the centroid location scale factors. So these were some of the important boundary conditions. Now getting to the loads, you can apply the loads now. So let's say I want to apply only two types of loads here. So load, go to static load cases to generate the loads here. Let's say self weight first, and among this you can select the load case type. This is important because when the program is generating the auto generating the load combinations, then it is important that you select the correct load type, because that particular load type will be used in the combination. Let's say UDL, uniformly distributed load, dead load, and add. And I want to assign self weight to the load case types SW. But first of all, I'll create a load group because I'm going to do the construction stage analysis. So I create a load group self weight, which will represent the self weight, and I create another load group UDL, which will represent the uniformly distributed load. Just right click and click new, and you can create a load group here in the group tab. In the works tab again, returning to the works tab, now you can go to load, self weight. Here you can select the load group SW, the load case SW, give a self weight factor of -1, gravity factor of -1, and using the mass density, program will automatically assign weight to the entire structure, and add it, close. So here in the work tree you can see that self weight has been assigned. Then go to load, element beam loads. Here you can generate a wide variety of loads, starting from uniformly distributed loads to concentrated loads to trapezoidal loads. It's very simple to apply. For example, if you want to apply uniform load, you can select the load case UDL, select the load group UDL, and from here I'll undisplay this hidden view, and now I select all the main girders here. I can provide eccentricity with respect to these girders in the y direction, let's say, and apply UDL of -10 kilonewton per meter. Apply. Similarly for this, an eccentricity of +0.3, and apply. Now if I see it from here, you can see that the UDL has been applied on both the girders. And now I'll model the construction stages for this bridge. I have defined all the groups. Before that, I have defined groups for boundary, I have defined groups for loads which I will be using in the construction stage. Now I need to define groups for the elements so that the program can recognize which element to activate in which stage. So first of all, I'll start with the assigning group to the main girders. So you can select the main girders like this, and with the main girders I want to select even these support nodes like this. You can select the support nodes too, and just drag and drop from here. You can see that this has been assigned to the main girders. Similarly, I want to assign a cross beam to this a cross beam group for the cross beams. So I select the cross beams by select by intersecting function. So select this option and click and just draw a line from here to here. So whichever points it in, whichever elements it intersects get selected, and now drag and drop. So this cross beam has been assigned to this cross beam group. And now let's model the construction stages. Load, construction stage analysis data, define construction stage, add. First construction stage, let's say 1, give a duration to the construction stage. This duration will be accounted for when the program is doing the time dependent material analysis. And you can, from the element group list, you can add the elements which you want to activate in this group. Give an age, since this is only steel girders right now, so age won't affect much. And then boundary, all the boundaries under this boundary group, add. And load, I want to activate self weight from the first stage itself, first stage, add. And then I click on apply. So my first stage gets generated. The second stage, where I am installing the concrete deck, so elements are the same, boundaries I have already activated, and I'll activate this UDL, uniformly distributed load, at the last stage, add, and click on OK. So both the stage has been created. I can create one more stage for seeing the long-term effect, long-term creep and shrinkage effect. So CS3, I can give a duration of 1000 days and just click on OK. This is to see the variation of stiffnesses in the long term. So after this, the program needs to know when the composite slab is being activated. So to assign composite section for construction stage, we go to construction stage analysis data, composite section for construction stage, and here we add. Now in this, the program needs to know the section type, that is the main girders from here. So active stage is stage 1, that is the first stage in which these elements were activated. And now you can select the part. First part is the steel and second part is the concrete. You can see in the diagram, you can assign a material name for the concrete, because the program now only recognizes steel girders, not the concrete. Now we enter concrete here. The stage in which concrete is activated is stage 2. Right now the active stage is 1, so I'll keep it as active stage. Age of concrete can be entered. This will be used for the creep and shrinkage calculation. Let's say 7 days. And you can see the stiffness scale, stiffnesses of each part. This is the part stiffness and this is the total stiffness. And this H is a notational size in meters. Click OK. This notational size gets automatically updated upon entry of the composite section. When you click on update all H, so this gets updated. The notational size which you entered earlier in the time dependent material properties will not be followed now. The new notational size in the composite section for construction stage will be followed now by the program. That is this notational size for the creep and shrinkage calculation. And now let's get back to the PowerPoint. So we saw self-weight, the application of self-weight. We saw then, yes, there is specified displacement which we can provide to the supports. We can provide some particular displacement and see the effect. Just right click, go to load, and go to specified displacement of supports, and choose the particular node to which you want to apply displacement. Enter the value of displacement and perform the analysis. Also, program can automatically generate the worst case in the settlement. So you can give settlement to multiple supports, and program will generate the maximum and minimum effects due to those settlements. And you need not create separate specified displacement cases. This settlement analysis data is useful in creating automatically the maximum and minimum effects due to support displacement. Then beam loads, the element beam loads. So you can provide many types of element beam loads. This is for if you want to apply for each element. If you want to apply for a set of elements, there are line beam loads. Just right click, load, and you can go to line beam loads. Similar to the element beam loads, you have option for uniform load or point loads and various other loads. And typical beam loads are special types of distributions available. Just right click, load, typical beam loads. So these are some of the special loads. Select any of them and you can enter the various dimensions and values of loads and enter the loads. Then uniform pressure, this is used to model the noise barriers on a bridge. Since they cannot be modeled in the program, since they are not the structural elements, so but still they play an important role in case of winds as in the form of lateral loads. So to model that load, we have option for uniform pressure. You can go to load, element beam loads. Here we can choose uniform pressure, and in uniform pressure you can provide the height of the noise barrier, the pressure, wind pressure, and a program will calculate the forces based on that. Then plane load option is used to provide any irregular kind of load on a plate. Normally on a plate we can give pressure loads by selecting load, pressure loads. So uniform distribution or a linear type of distribution can be obtained. But let's say you want to only apply a point load at the center of a plate or anywhere on the plate, then you can go for load. You can define the plane load from here. So whether point, line, or area, define the coordinates on the plates where you want to apply the loads, and you can apply loads at any point on the any area on the plate can be loaded. Then a variety of temperature loads can be inputted in the model. You can input uniform temperature to the whole system by system temperature, to different nodes, to different elements, and for special sections like PSC and composite type of sections, we can apply beam section temperature directly by providing temperature. This can automatically simulate the temperature gradient. How to do that? Right click, load, temperature loads, system temperature, nodal temperature, element and beam section temperature. For example, if you go to the beam section temperature, you have to just select the beam, select the type of beam, PSC, composite, or general beam, and like here you can see H1, H2, T1 and T2. So for each height you can give the temperature, and in that manner temperature gradient can be modeled automatically. Then at the abutments you can model the soil pressure, the hydrostatic load. Go to load, and in the load go to hydrostatic pressure loads. You can model the surcharge on the soil in backfill, and the hydrostatic pressure can be generated on the abutment. Okay. Now after defining the static loads, now we are moving on to the moving load analysis, that is applying vehicles and performing influence line analysis and influence surface analysis, and determining the maximum and minimum effects due to the moving load and the vehicle positions which cause those effects. That is again a simple step, three-step process in the program. So just right click, load. The first step is choose the code, let's say Eurocode. Okay. The second step is to assign the lanes on which you want to run the vehicle. So traffic line lanes, moving load analysis data, traffic line lanes, add, give a name to the lane, lane 1, and you have to generate this lane with reference to some beams. So the eccentricity can be entered from here. So let's say wheel spacing can be entered between the for an axle, and the lane width can be entered. If there is any area loading, program will calculate the loads based on this lane width. If there are wheel spacing generates 2 influence lines per axle based on the wheel position and the spacing. So there is also vehicular load distribution that you can provide in a lane. So if you select lane element, then this is how it will affect. If you select lane element and you have generated, this is the cross-sectional view. So if you have generated the lane with respect to this beam, then only this beam will be applied with this wheel load with a load and a moment, load times eccentricity. If you have selected cross beam type of loading, then if the load is applied here, it will be first distributed to these adjacent girders using the cross beam type of distribution through these cross beams. So here we have provided cross beams, and let us distribute this load via cross beams. So select cross beam, and the cross beam group which we had created for the cross beams can be used here, and select by 2 points and just select from here to here and click on OK. You can see the lane has been created. These 2 dots which you are seeing here represents the wheels. They are spaced with 2 meter spacing, and the center line shows the center line of the lane. And now after defining the lanes, we'll define the vehicles to run on these lanes. Add standard. Let's say I want to define only one vehicle on this lane, load model 1 type, and automatically you can see all the adjustment factors and axle loads here. And now assigning the loads, the moving load vehicles to the lanes which I defined earlier. So load, moving load analysis data, moving load cases. So when I define the moving load case, it is actually assigning the vehicle to a particular lane. So you can select the type of load case, load model 1, and from the list of the lanes you can select it under the selected lanes category and click on OK. So now this vehicle, load model 1 vehicle, will run on lane number 1. Similarly, you can create a number of lanes and apply vehicle loads to this. Sometimes for some codes we have the option for combined and independent loading. If there are 2 lanes on which there is vehicles running and another there is, let's say, some other vehicle like train running, and we want to take the combined effect of both of them on the bridge, you can select the combined option here, or if you want to treat them as independent, then you can select the independent option. So you can see for this type of loading which I was talking about, let's say if you add, in this case you need to define 2 lanes, and you can see that uh, if you press on combined option, then you define 2 load cases here and they will be selected. Both of them will be considered for taking the worst effects. So then after this we need to enter the load combinations. Before entering the load combinations, let's just define the analysis controls. For the construction stage analysis control, we can define through analysis construction stage analysis control data. Here you can see that there are many options. You can include nonlinear analysis in the construction stage itself. You can include time dependent effect, that is creep and shrinkage effect, tendon tension loss for the long term, for the time dependent losses can be considered from here, and several other options. And here you can also choose which load case you want to distinguish from the construction stage dead loads. Let's say if you have a number of load groups which you have used in your construction stage, all of them except the pre-stressing loads are grouped under a load case known as the CS dead load. And let's say if you want to see the effect of only one particular load case, then you need to separate it out from the other loads here. Let's say I want to see the effect of UDL, then I separate it out here and add here, and now I click OK. So I'll get another load case known as CS erection, under which I can see the effect of the UDL. Then I also want to do the moving load analysis, so I need to give the moving load analysis control. From analysis, moving load analysis control, I can select the load point selection, influence line dependent point, or all points will be considered for the loading. And here I can click OK, and now I can run the analysis by clicking on this button or press F5. So this analysis is completed, and after doing the analysis, you can combine the results. So I want to do the composite plate girder design later on. So select steel design from here and auto generation of load combination. Select the load case, Eurocode, and select OK. So you can see the automatically load combinations are generated, and you can see the various scale factors, load factors. Here you can change the type of the load combination from ULS or SLS type, that is strength check, whether you want to do strength check or subversibility check. You can check it from here. Close. Now to see the results, just go to this post-processing mode. So this is the pre-processing and this is the post-processing mode. Go to results. You can see the reactions here. Let's say for the self-weight, this is the final stage after construction. So the reactions can be seen due to self-weight. You can see the reactions here. Deformation due to the self-weight can be seen with the legend. Let's see the stage-wise results. So select the stage from here. Let's say I want to see the beam diagrams. So you can see these are the stages, these are the cases that have been created. CS dead represents the self-weight in this case. CS erection represents the UDL, which CS erection will consist of any load which we have separated out. So in this case it is UDL. Then creep secondary effects, the secondary effect of creep due to indeterminacy in the structure. Then summation is the summation of the creep, shrinkage, and the dead and the erection loads. In case if we had used tendons in the pre-stress for pre-stressing, then there would have been two more load cases for tendons primary and tendons secondary. Let's see the dead load, that is self-weight. And here you can select the part for which you want to see. So if you select total, then by default the part which is part of the composite section which is activated in that stage, only that result will be shown. So for example, in the first stage we have only part 1, that is the steel girder, and if I apply here, this is the bending moment diagram with the deformation. And if I change the stage, can see there is change in the values when the slab is activated. And for the erection load, for the stage 2, there is no load because there is no UDL, no movement. And when in stage 2, there is no separate movement in the part 1, but if we see total, in the last step we had applied the UDL, so you can see the effect due to UDL in the last step of the stage 2. Then if you want to see the creep deformation due to creep primary deformation in the last stage, apply, you can see the undeformed shape. This gray line is the undeformed shape. You can see the creep deformation in the last stage, and in that particular stage the deformation due to self-weight, you can see this is a deformation due to the self-weight. This is the deformation due to the creep due to composite action, and due to shrinkage you can see the deformation here due to shrinkage, and so on. Then we can also see the beam stresses for the construction stages. We can see stresses, beam stress diagrams. Let's say for dead load, we want to see at the bottom fiber, stresses at the bottom fiber. For part 2, that is in the steel, in the concrete, let's say the top fiber of the concrete. This is the beam stress diagram, stress variation at the top fiber of the concrete slab, and at the bottom of that is the bottom flange, steel flange. This is the variation of stress. All these results can be seen in tabular format by going to results, result tables, and here you can choose the type of the result you want. Force and stress, select the load case, okay, and this is how you can obtain in the tabular format. You can copy this in Excel for design purpose later on. Also you can see the stage-wise composite section results in the result tables. Composite section for construction stage, beam force and stress. So for the construction stage you can see part wise section part, top and bottom, the slab and the girder. You can see the axial force, moment, and the moment Y and moment Z. Similarly, beam stress can be seen. This is useful for doing the elastic limit check, elastic stress limit check at each construction stages, because there will be changes in the there will be stress distribution when we activate the composite slab. So it is necessary that the stresses fall under elastic limit before and after composite. If we had used tendons, we can also see the tendon time dependent loss graph. So I'll open another model to show you how tendon time dependent loss graph can be seen. Okay, this is a balanced cantilever bridge, and here we can see the tendon time dependent losses. Select any construction stage. We have used tendons here. You can see in the results tendon time dependent loss graph, and select the particular stage. Select the tendon. So the tendon was activated first in this particular tendon was activated in stage 13. This is the tendon force, and gradually with losses the variation can be seen. A detailed tabular format can be obtained from result tables going to tendon and tendon loss. Here you can select the tendon group and select the stage, apply, and it will show the loss of the tendon up to that stage. Relaxation, creep and shrinkage loss, elastic deformation loss. You can also see the bridge cutter diagrams. This is used to get an overall idea of the stresses inherent in the bridge during the construction process. So you can select the load case type, summation let's say, and select the complete bridge cutter for generation of the stress. Let's say I want to check the maximum stress in the section and compare it with allowable stress lines. So this is my stress distribution along the length of the bridge. This is the length and this is the stress axis, and these dashed lines are the allowable stress lines, and you can see these stresses lie within the allowable stress lines. So during the construction, at this construction stage, the structure is safe under these elastic limits. You can also check the force in the bearings by going to results, result tables, elastic link. You can choose the load case and see the force in the bearings, the axial force, shear force, torsion moment, etc. on the elastic links. So now moving on to the design part. Let me open another model. I want to show you the composite plate girder design. For example, this is a full scale, full model composite section. A similar manner, the modeling has been done in similar manner as I showed you. Moving loads, and you can see composite section applied, composite section for construction stage, just like in that previous demonstration. Construction stage analysis control, moving load analysis control, both have been applied. And for the design, composite section design, we go to results, combination, create a combination in steel design category, and this is how the combination is generated by auto generation. Then after that we go to design, composite steel girder design, and enter the design parameters here, the various partial factors, and then design, composite steel girder design material is chosen. Select this material and you can select the steel and the concrete material that we want to choose for the design. Then we go to reinforcement definition. You can define reinforcement from here. Line type, just by drawing a line like this, and entering the rebar specifications. And this manner the rebar will be entered. And we can also enter various other data like lateral torsion buckling data or the transverse stiffener data can be entered, selecting the elements and entering the data. And then we can choose the design position, which element to design, select the element and which position to design, I or jth part of the element. So after this we click on design and the program starts the design process. And to generate the detailed Excel sheet for the to see the calculation for the design, we can go to print result, click on print result, and this is how you can generate the Excel sheet. The Excel sheet is generated, looks like. So you have the section information, before and after stiffnesses, resistance to vertical shear, resistance to bending, lateral torsion buckling. This can be seen. Then we can see the results in the tabular format. Design result tables, bending resistance check. So here we can check if it is okay or not, section is okay or not. So if it is blue, that means it's okay. If it is red somewhere, then it is not okay. Here it is, everywhere it is okay. The capacity is more than the applied moment. Similarly, resistance to vertical shear and so on. Similarly, you can also perform the PSC design for PSC type of bridges. Yes, the process is the same. Design parameters is selected, entered, and PSC design material is entered, design position is entered, and PSC design is ran. Now I want to show you how to see the moving load positions for the maximum and minimum load effects. So coming back to the original model, to see the influence line diagrams for the moving load analysis, go to moving load tracer, go to influence results, influence lines. Let's say I want to see at this element, the moment influence line. This is the influence line for that. You can see for a lane we have two influence lines. We have two influence lines, the bigger one and the smaller one. These two lines show the influence lines which represent the wheel positions. Then we can also see the position of vehicles causing the maximum moment at the particular element. So moving load tracer, beam forces moments. and just click on apply, and you can see this is the vehicle position which causes this moment, maximum moment at element number 5. You can convert this moving load into a static load later on by clicking on write min max load to file. Click OK, and the command format is obtained. Select everything, copy, and go to tools, mct command shell, paste it here and run. So you can see in the works tree now there is another load case, and if you display it you will find that this is the same as the moving load obtained from the moving load tracer. So this is how you can convert a moving load into a static load. This is useful when you are trying to see the concurrent forces, concurrent reactions. So using this you can see the reactions at all the four supports when there is maximum bending moment at the element number 5. You can see the concurrent reactions. So this brings us to the end of today's presentation, and thank you for attending it. If you have any questions regarding the presentation, you can put up the questions now. Um, Mr. Yaman Wadhwani has a question here. The question is that can we see the real displacements in the model, that is the real displacements for the construction stages? Well, yes, in the program you can see 3 types of displacements. So when you select the construction stage, and if you select here, and if you reanalyze it, in the construction stage analysis control, you have option for initial tangent displacements. If you select this option and click OK, and now if you check the deformations, let's say for stage 1, so you can see there are 2 options: current step displacement and stage step real displacements. The current step displacement will show the displacement due to the loads only in that particular step, in that stage. So this is the displacement for that step only. And in stage 2, if I go, this is the displacement for only stage 2 loads. But when I click on real displacement, this will show the actual displacement of the structure in that stage, adding up the previous displacements. Similarly for stage 3 you can see the real displacements. So yes, you can see the real displacement in the structure. You can choose whether to see the real displacement or the current displacement only. Okay. Okay. Okay, since there are no more questions, so if you have any questions, you can always mail us at esupport@midascivil.com. I'll send it in your message window. So you can mail us at esupport@midascivil.com and we'll be very happy to support you. So till then, see you. Goodbye.